All right, so this is 127, and I was going to have a guest lecture today, but that's going to be on Thursday instead, so I'm glad a lot of you got the message and came to class. And so I'm going to talk about 64-bit assembler. That's where we are. Intro to 64-bit assembler. So let me bring my slides in. Oh, and by the way, speaking of guest lectures, we got one coming up on April 12th from Caitlin, who just got the OSED, which is the certification that would come from this class. The certification in exploit development. First person I know that's got it. I don't have it, but she got it and she can talk about it, and that will be very interesting. So I highly recommend that. She's a lot of fun too. She's always a very popular speaker in my classes. So, all right, so 64-bit assembler. The first thing about 64-bit code is you have a lot more registers. Instead of just A, B, C, D, and stack pointer and the instruction pointer and such, you have the usual stuff you'd find in 32-bit code, plus a whole bunch more, 8, 9, 10, up through 15. This helps the efficiency of code you write. In 8-bit or in 32-bit code, you often have to struggle because there aren't enough registers, and so you're shuttling things to memory. Yeah, the space hacking class that Caitlin has is also in the big hit. Yeah, all of your stuff is a hit. And so now, just as in 32-bit registers, you can refer to smaller registers inside the registers. So the 64-bit register is called RAX, but you can use EAX, the same thing we've been using in 32-bit code, which is the lower half, and AX for the lower 16, and AL for the lower 8. So you can refer to 8, 16, or 32 bits at a time if you want to, although most of the time, of course, you just use the whole register and refer to 64 bits. All right, now this is something that surprised me. Even though the data processed by an instruction is 64 bits, the address does not use all of the 64 bits. So now 2 to the 32 bits is 4 gigabytes. And that was one of the main reasons why everybody had to move from 32-bit computers to 64-bit computers, because 4 gigabytes, well, quite a bit of RAM is not really a lot by modern standards. So moving to a 64-bit processor would be a way to handle more RAM without artificial things like paging. And I thought you could go to a full 2 to the 64 bytes, which would be some enormous number of bytes, but you don't really need that. And so Windows 10 only uses 48 bits for the addressing. And that means you can only go up to 24 terabytes of RAM, which is not the full 2 to the 64. It's enough probably for the next decade or so before very many people can afford more than that. And on you go. So you're only using 48 bits for addressing. And that means, and there are different versions that can go to different parts in older versions of Windows. But another thing that is very strange about it is that the actual available memory is split in 2 halves. So with 48-bit addressing, you have a high half of memory where the addresses all start with 4 Fs, and you have a low half of memory where the addresses all start with 4 or 5 zeros. 4 zeros. So it's not even contiguous. You have a bunch of it down here at 0 and a bunch of it up here at F, and all this stuff in the middle is illegal and unreachable. You can't actually get to those addresses. So that's kind of screwy. And I think there are some OSs that use 56-bit addressing, which gives you a little more. But again, still splitting to a high half and a low half. So that's how it works. So you use syscall instead of int80. And so that system call will make your kernel call, and now it uses a whole bunch of registers to pass parameters, RDI, RSI, RDX, and so on, to pass the arguments. You pass the number of the system call in RAX, up to 6 arguments in these registers. No argument is passed on the stack, and then you call your system call. All right, so there's a link to syscall's table, and here's a few of them. Syscall 0 is read, syscall 1 is write, and here's the details of how it works. You can write, and so you have an unsigned integer for RDI. This is the number of bytes to write. Here's a pointer to the string, which is the characters to write. Oh, here's the size. Oh, excuse me, this is the handle of the device to write to, I think. This is the size, the string, and this is the size of the string. All right. So you can find more details about the registers online with this assembly zone with all the details of all the registers that are there. But we don't need to know more about them for what we're doing today. And then there's common opcodes. The 64-bit opcodes are very much the same as the 32-bit opcodes. Move, exchange, add with carry, multiply, divide, increment, negate, rotate left, rotate right, jump, jump equal, jump not equal, and a loop command you can use. They're pretty much the same commands that have been in everything all the way back to the 8-bit days. All right, so here's syscall1 write. So if you want to write text to the console, this is what you have to do. Set REX to 1 to show that you're doing the write call. Set RDI to 1, which is the file descriptor for standard out. If you wanted to write to a file, you'd have to first open a file, and then you'd get a handle to that file, which you'd put in here. Push the string onto the stack. Now set RSI to RSP, so it's pointing to the top of the stack where you just pushed something. So that's going to be a pointer to the string. Then set RDX to the length of the string, and then execute a syscall. So this is like we've done before, looking at the structure of shellcode and assembly code in general. So let's make some programs, and I've got them all here. ABC1. All right. So here's my Debian machine. And all right. Looks like, yeah, that'll do. I know it looks like I'm not getting the bottom correctly on the screen. There we are. All right. So let's look at abc1.asm. All right. So here we go. You have to tell, there has to be a text section, which is where the code goes, and this program has nothing except a text section, and there has to be a start symbol, which tells it where the program starts. If you don't do that, it will start at the beginning of the text section, which would be all right, but it is unprofessional. You'll get an error message. So you put a start here. Now that's where it should start. Now I'm going to move this number in REX. This is what I want to print. This is A, B, C, D, E, F, G, H in hex. So that's a 64-bit number. I put that in REX and push it on the stack. Then I put in RDX8, which is the length of the thing I'm printing. I put RSP in RSI, which is a pointer to the string. And I put 1 in REX and 1 in RDI. One of them is the syscall. This is the syscall number, which says write. And this is the file descriptor, which is file channel 1, I forget the correct term for it, which is sysout. So that's what you do. Now to compile this thing, you do this. You have to have YASM, which you can install with sudo apt install, and then first you YASM -f elf64, which means make 64-bit object code out of this, and that creates ABC1.0, and then you link it with LD, creating the full output of ABC1. So there's 2 steps, compiling and linking. And now we can run that thing. And you see it does print this string. And remember, we should be used to this by now. It's going to print backwards, 876. So it's HG back to A. Strings do print backwards because they're stored little endian. And so this least significant number here goes first. So the H is first. And then it just crashes because I did not exit. I just ended, and so it's going to have a segmentation fault. It cannot return back to the operating system cleanly. It just crashes. So to fix that, let's put a proper exit in it. So this is all the same, the syscall to print something, and here's the syscall to exit, 3C. So you just put 3C in REX. You don't need to change anything else because it's not going to look for any parameters, and then do a syscall. So ABC2 will not crash. It will exit normally. Now, I didn't even put a carriage return in my string, so it's just going to sit there, but still, it comes back without crashing, so that's a little bit nicer. All right. And there's the exit, which is 60, which is 3C 48 plus 12. All right. So now let's put the letters in order. That's ABC3. So that's here. right, now all I did was rearrange the letters here. 1, 2, 3, 4, 5, 6, 7, 8. Now the least significant number is going to go first, which is 41. So this one, we'll print them in order. A, B, C, D, E, F, G, H. So that's good. All right. Now we're going to use a data section, and that's going to be hello.asm. So let's take a look at that. All right. Now I have a text section down here, but now I define a data section, and I put a string in there, defining it as a bunch of bytes, and you can just put in ASCII characters in quotes, and it'll turn them into appropriate bytes, or you can put numbers in, and the 10 is a carriage return, or a line feed. I forget which one. It's I think it's a line feed. It's the appropriate way to end a line in Linux. So now I've got a string, and it's 5, 10, 11, 12, 13 characters long. So now I have the same thing down here, except now the length of the string is 13, and the pointer to the string is the double word pointing to string 1, which is the 64-bit address of this variable string 1, instead of pushing it on the stack and using RSP. So now I've got a pointer to it, I can print it and then exit. So this gives me hello world with a carriage return. And it does. So we're getting a little bit better at making something in assembler. Now let's take a look at the structure and security of this thing with objdump -h. Objdump lets you see what's inside there. And I think it's first H. Yeah. So here you see the sections. Now we see up here it has a data section and a text section. And this is how the executable is laid out in memory. The text section goes here at 401,000 in hex. Remember, every program likes to run at 400,000. That's where it naturally wants to be. So the header of the file is at 400,000, and the actual segments start at 401,000, and it spaces them out. So that's why there's aligned to this number. So this one starts at 401,000. That's the text. The next one starts at 402,000, and that's the data. So that's what objdump shows you with -h. And we can learn more with objdump -x. So let's do that. Objdump -x will show us a lot more information about the file. It is a 64-bit executable. For Linux, executable link format here is the Linux format, the analogous to a PE format in Windows. And I see a whole bunch more pay what you can classes. Good. I'm glad you found them. All right. So then down here it has the start address, 401,000. Here it has all three segments. Here's the first segment at 400,000. Here's the 401,000, which is the text section, I think. Yep, the text section here. And here's the data section. Now this is getting a little interesting. This part here is the header, and it is read only. Memory has permissions, because when you allocate memory, you specify what permissions to give that memory. So this memory, it's read, write, execute, just like everything else in Linux. So this header is read only. You can't change any of it. This is read and execute. That's the text section that contains the executable code, and this is read, write, but not execute. And a fundamental security principle is write or execute. No memory segment should be allowed to have write and execute at the same time, because that's what makes it possible to do the classic buffer overflow that we've been doing, where you write on the stack and then you execute code on the stack. So to prevent that, all modern systems will not like to let you write and execute for the same memory segments. You can do it, and the programs we've been using have been arranged to create that unsecure situation, but by default they avoid that. Here's the same thing we saw before, the two sections. And by the way, you see an alphabetical description of security here, read only for text, when it's really read and execute, so I think that's perhaps a little funny. And here's the data. So here's more information about where they start. Here's all the symbols, text and data section. Here's the start point, pointing to 401,000. Here's where the stack starts, 402,000, basic stack segment, and so on. So, all right, that's more information you can get from objdump about your program. And now we can use GDB and do info proc map. So let's try that. If we run GDB in quiet mode on hello, it starts. Now if I try to do info proc map, it's going to tell me no process is loaded, which is annoying. A simple way to fix this is to do start I. I don't know why they make you do this, but start I will run the program and break at the first instruction. Now it is loaded. Now I can do info. So see, it went to the start of the program, 401,000, and it stopped there. So this just put a breakpoint at the first step and went there, which I think the Windows debuggers do this by default. And I don't know why GDB doesn't, but anyway, you do it with start I. Now you can do info proc mapping, and now you'll see the same story. There's 401,000, 402,000, and 403,000 are segments of the hello. The stack is down here at 7FFF in high memory. And so here's low memory and here's high memory. All right, so there are the various segments of the code running. And you can see the ELF header. We can now see, for example, there was something at 400,000. We saw it before. There is a section at 400,000 itself, and I sort of wondered what was there. And let's do X and S. X, let's take a look at the start of that, of 400,000. All right, so it does have some data there. Here's a 1 and a 2, and here's what looks like some ASCII. So it would be good to look at it as characters, I think. Yeah, or strings. X/4 strings, 0x400,000. All right, and so this is ELF. This is, remember, every PE file starts with MZ, I think. There's a few characters that start to indicate that it's a Windows portable executable. These files start with ELF, with a 7F and then ELF. And here's a couple of, a 2, a 1, and a 1. I don't know what they mean, but they're more part of the ELF file header. And notice here is a pointer to the text section, probably the starting point, and so on. So header information is here, just like PE header. And we can look at the other sections. The start function, if we look at X, say 20X, 0x401,000, that is the text section, so it's really just looking like random numbers here. You should be viewing that with as instructions, and you could do it this way. You could just view instructions with I, and then it'll show you some of the instructions, and you can see this is the whole program we wrote. Since we wrote an assembler, it's just going to directly be the code we wrote, and here's, I think, just nulls. Or you can use disassemble start, and that will show you the function without the extra junk at the end. So that's at the 401,000, the text section, and you can see it's wasteful of memory. It took these little short segments and spaced them out because it likes to put them on even thousands. And 402,000, yeah, we can do that with just characters. Let's try, whenever I don't know what's in something, I first look at the raw hexadecimal. So 0x402,000. All right, and this looks like readable ASCII, 48, 65, 6C. Those look like ASCII, so it would be good to do X/strings perhaps, 0x402,000. Yep, so that's where the hello world is stored, and after that, nothing else. So that's the data section. All right, so you can see how your program is laid out in memory, and we can look at the registers, which is info registers. You can abbreviate it. All right, and so most of the registers have nothing in them. The stack pointer points here to the start of the stack, which is up in the high memory region, and the instruction pointer points to the start of the program, which is here at the start pointer in 401,000, and there are a couple other registers that have things like, these are just segment registers, which you don't usually have to worry about. All right. So now we can use read. All we've done so far is write and exit, so now we can read. So we're going to make a program called read, and let me just bring it up live and talk about it. Let's get out of here, and cat read.a, oops, all right. So now We make a data section, and we just put some data in here because we're going to read data into something, and this is just one way to reserve space. I'm just going to fill it with filler letters, 11 letters. Then I have a thing called string 1. Now I go to start. Here's my start. So I move into RAX 0. 1 is write and 0 is read. So this is a read. I have going to read 10 characters from the standard input, which is device number 0, and I'm going to put it in string by putting a pointer to string and RSI. So this will read up to 10 characters from the console, and this will then write 10 characters of string 1, and this will then exit normally. So what we're doing here is recreating about 3 C commands in assembler. And so that's read. All right, so if I give it hello, it returns hello, enter, because I put in an enter, and then it has some leftover junk, BBCC, because I put it in here, HELLO, enter, and you have a BBCCX left over, but I only printed the first 10 characters, so I didn't print the X. So that can read something and echo it back. It's a little sloppy, but at least it didn't crash. All right. So now we can make the Caesar cipher, sort of. Let's take a look at this one. All right, so now I'm going to set aside space for 8 characters, and now I'm going to read 8 characters from the console, just like before, so I can read up to 8 characters of plain text, and then I'm just going to add 01010101 to it, so that'll move everything forward 1 letter in the alphabet, and then I'm going to print that out. So this is an attempt to recreate a very simple Caesar cipher where you move all the letters forward 1 in the alphabet. So let's see how well that works. If I give it ABC, it turns it into BCD. So that's pretty good. Okay. If I give it XYZ, it turns it into YZ bracket because I didn't include wrapping around to A again. So my Caesar cipher has the defect that it gets the wrong answer for Z, but it has another defect too. If I give it hello, it changes the H to an I, the E to an F, and the L to an M, but it does not change the O. Now, the reason is, when you compiled it, which I didn't do live here, but I think I have it on the slide, when you compile it, it's going to warn you, value does not fit in a 32-bit field. The problem is, if you look, let's look at obj dump minus D to look at the actual assembly code created here. Obj dump minus D of hello. All right, notice here, wait, not hello, but Caesar, that's my problem. All right, notice this instruction. That is the instruction that I actually got. But if I cat my source code, this is the instruction I wanted. I wanted to add a 64-bit number to RCX that contained 8 01s. But what I actually got was only 4 01s. And that is because the 64-bit Intel instruction set does not include this operation. You cannot add a 64-bit immediate value to a 64-bit register. This is a gotcha. There are 10,000 instructions, but you're not allowed to do that. And that's what it was warning me, saying you can't put a 64-bit immediate value in this command. I'm only going to put a 32-bit immediate value in that command. So it's only going to increment the first 4 characters and no more. So if I want to actually make it work, I need to write my program another way. And that's what I have here with Caesar 2. Now, instead of trying to add a 64-bit value right into a register, I put the 64-bit value in a register, and then I add a register to a register. And this is legal. You can put a 64-bit value in a register. You can't add it to a register, but you can put it in a register. And you can add a register to a register, and that's a 64-bit operation. This is one of the gotchas of assembly language. Even with 10,000 instructions, simple things that you think you can do are not there. You have to stick to instructions that exist, which is, of course, why almost everybody would rather write C code and run a compiler, where the compiler will carefully choose instructions that exist rather than writing your own code in assembler. But anyway, now this one will work. That's Caesar 2. And so if I give this one hello, it changes that O to a P. This will work for up to 8 characters. So that's a little gotcha. And you'll find it if you go online to the developer's manual. You will see there is add register 64 to register or memory 64. And there is add another one here. But there is no add immediate. Here's the add immediate. Add immediate 8 to register or memory 16. Add immediate 8 to 64. Here's add immediate 32 to 64, but what you do not have is add immediate 64 to register 64. And by the way, if you write ARM code, it is much more restrictive. That's the whole point of ARM. It's a reduced instruction set, so you have to pretty much always put everything in registers, do the math in registers, and then put the output back in memory. It doesn't have hardly any of this direct-to-memory stuff. All right, so that's how you do it. And now you've got a working Caesar cipher that works up to 8 letters, and it still has that problem of Z not wrapping around. So we're making very primitive code here. The code we're making here still boils down to like 3 lines of C. All right, and so there's a project where you do this ED220, and there are some extra credit flags at the end you can get by writing more little assembler code, and that gives you a little bit of practice writing 64-bit assembler. So let's take a look at a Kahoot. And here it is, L7. And this is why when you make shellcode, even if you make it with Metasploit, it's fragile stuff. Little tiny details will make it not work. So I've spent a lot of my life trying to figure out why my shellcode doesn't work. It's finicky, picky stuff. Shellcode offer any error messages? No, typically not. In this case, I got one message while compiling, but usually it just crashes. And that's because shellcode is optimized. You would have to program in the error messages, and shellcode is always shrunk down to the smallest number of bytes, so usually no error messages. It just fails, and you have to figure it out. That's why, everybody prefers to use high-level languages, like Visual Basic and Python and C. Writing shellcode is for the hardcore. You're playing with no net. All right, I'll give it a few more seconds. All right. All right, how many bits in AL? Yep, the low bit is 8 bits. This is the lowest 8 bits of the 64-bit register called RAX. All All right, how many bits in RAX? Okay, and it's 64. This is the full 64-bit register. All right. All right, how many bits does Windows Server 64-bit use for addressing? Yep, it's 48. Kind of screwy, but that's the way it is. All right, if the Intel set does not have the 64-bit instruction you want, how do you do it? Yep, you use two commands. You can, of course, do anything. It is NP complete, all programming languages are. You can do anything, but it might take several commands to do it. So, all right. All right. All right. Good. All right, let me stop that recording.